Hi gang, I started the recording already for once. How is everybody doing? All right. So today, let's see. Today we're basically going to talk about cooling, but before we get to that, let me mention today I have office hours scheduled at 3, but I have an appointment at 2, and I think it might run over a little bit. So I'd like to take that to 4 p.m. Just so I'm there and give you a chance to go over things. I hope that's okay. If it's not, I'll be very flexible. I have lots of time after that, even this evening and tomorrow morning in case you need to go over anything. I don't think this problem set that's due today is super tough, but if you know, you want a chance to go over that, then I'll certainly give you time, 4 o'clock or later, to go over that. Friday, I'm thinking Friday we might have some sort of problem solving day. Now that doesn't mean that I don't want you to come. It's not really going to be a review session, but it's going to be something maybe where I give you all a problem or two to solve and you kind of work together on it. And we'll see how that goes. Both because I looked at the schedule. I think we have a lot of flexibility before the next test. And like I said, like I've said before, I want to give you guys a chance to kind of work through some things together, because I think that's beneficial. And then next week we'll work on chapter 7. I'm feeling a lot of feeling out some new not really a schedule, but kind of a new order of doing things this semester. And so I just want to try a couple things out, see how it works. Today, we'll talk about cooling and cryogenics. This is really about how do we attain very low temperatures. And preparing preparing to use this book and reading some stuff, I found out a lot about this guy Joke. This guy's name is Joke. It's pronounced Joke, right? And he was Canadian, but because his father was an American citizen, even though he was born in Canada, he was an American citizen, and he's a really kind of brilliant guy, and he, as a lot of people do, he kind of just accidentally, a couple happy accidents got him to Berkeley about 1920. He stayed there his entire life, and there's a lab building. There's a building at Berkeley, and if you've never been to Berkeley, sometime you should go to Berkeley and just see the chemistry department, because it's kind of a little city almost with the buildings. The buildings are all connected. There's basements, sub basements, and you can get from the top of one building to the bottom of another without ever seeing daylight, which I think is the way the professors like the graduate students, you know, to be never seeing daylight. And they're doing some new building there. But anyway, one of the labs is the Joke lab, and the Joke building, the Joke laboratory building. And it turns out that he pioneered a lot of this low temperature stuff, which is actually pretty interesting thermodynamically. And we've done some of the manipulations, the Joule-Thompson manipulation and getting that coefficient stuff. But now we're going to talk about how this works a little bit. So to start, let's talk about how would you just cool a liquid, right? The one way you can cool a liquid, just let's say a conventional liquid, is you have the liquid and then you have its vapor above the liquid. You can put this in an insulated container, adiabatic you would call it, right? And you would pump out the vapor. If you pump out the vapor, then what you're going to do is you're going to disturb the equilibrium between the vapor phase and the liquid phase. Normally, the vapor phase and the liquid phase are in an equilibrium where the condensation equals the evaporation. But if you pump this out, you're influencing, or you're creating more pull, you know, you're evaporating the liquid, and this will cool the liquid, because the only place the kinetic energy can come from to do this is the liquid. So the kinetic energy of the liquid gets lowered, and thus the temperature gets lowered. Actually, there's kind of a interesting thing that happens in some of the work that I do, where I look at simulations of aqueous droplets of salts, of simple salts, right? And if you put a droplet and do a computer in a vacuum and just do a computer simulation, the water boils away, starts boiling away. But as it does that, it carries away kinetic energy, which lowers the temperature of the droplet that's left. And if you don't do something to maintain the heat of the droplet, right? In other words, simulate some ambient temperature, the droplet basically freezes and no more water will evaporate. So you get what's called a flying ice cube. Even though it technically is the right temperature because of the kinetic energy like this, the kinetic energy within the droplet is below freezing. So you get a frozen droplet. So anyway, this is basically how you can cool a liquid, right? And this is basically refrigeration. That's a refrigeration process. In order to cool a gas, you do something called throttling, gas throttling, right? And rather than try to draw this, I'm gonna use this picture grabbed from our text. right? So we have this picture here. So this picture bears a little bit of discussion because it can be confusing. Basically, what you have is let's say a glass tube or a tube, you know, and that's the volume of the container. And this picture just shows a small portion of it. And what you have in the middle is a porous plug. So the gas can diffuse through this, but at a reduced rate, right? So what happens is that the pressure on the right, once you squeeze the gas from left to right, the gas on the right has a lower pressure. And if you make this adiabatic, in other words, if the tube is insulated by styrofoam or whatever that doesn't allow heat transfer, then the temperature will be lowered, right? Because as the pressure goes down, the temperature has to go down. So this is called throttling, gas throttling. Now, it's important to realize that in these pictures, these shaded regions are virtual regions, okay? So these are virtual volumes. In other words, they're not closed. They're going to be virtual volumes that we use to visualize this problem, right? And maybe the way to think about them is fixed n, right? So if you look at the picture in A, V1 prime is a virtual subdivision of the whole volume on the left-hand side, right? And it's at T prime and P prime, right? So that's V prime, but it's V1 as in before. The one means before, the single prime means the left side, the double prime means the right side, and the 1 and the 2 means before and after, right? So that's the convention here. 1 before, 2 is after. Single prime means left, double prime, single prime means left, double prime means right. So that's the convention here. And the shaded volumes are just virtual, and you can think about them as fixed number of moles, right? So when we start off on the top, we have V1 prime, and we're going to think about how that volume changes with time. Well, it's going to be reduced because we're going to squeeze some of the moles out to the right, right? So V1 prime to V2 prime goes down, right? V2 prime is going to be less than V1 prime, the left-hand volume, as we squeeze gas to the right. Conversely, V1 double prime, this virtual volume on the right, is going to be lower at the beginning and greater at the end, right? Does that make sense? But these are just samples of the total volume that we're looking at, right? Okay. So let's think about the conditions. We have T prime and T double prime. We would expect T double prime to be lower. And so what we imagine is something like this, right? Here's the X position going through this tube. And here, we're going to have the plug, right? And if we have T prime and P prime over here, this is really going to be the pressure versus the displacement. But here we have P prime, and down here we're going to have P double prime, which is also going to be T double prime, right? And so what happens is, on the left-hand side, we're going to assume that the temperature of the whole left-hand side, left of the plug, is constant. So it goes like this. And the temperature on the right-hand side, after the plug, is also constant, but it's going to be lower because of this expansion, right? Lower pressure is going to give us a lower temperature, so it's going to cool. So it's going to be like this. And so what we assume is that the entire gradient, all the change is going to happen basically in here, right? So I think it's important to kind of go through this a little bit to make sure that we understand, because it's not easy. It's not easy to understand what all this is happening. And what we assume, or what seems to make sense, right, is the temperature is going to go down. So then this V double prime volume of gas is going to be at a cooler temperature than the V single prime volume of gas. And maybe the way to think about this, again, is fixed amount of moles moving through the plug. Okay, so the work, let's think about the work in this system. Well, first of all, delta U is Q plus W, but because of these adiabatic walls, Q is 0. So delta U is the work. So if we know the work in this system, we know the delta U. So that's pretty convenient, right? So let's figure out what the work is. The dW is minus P, right? The applied pressure on either side, which we're going to refer to generally just as P here. The area of the piston, right, times the displacement, delta X. So the X direction is going like this. Okay. Well, that's the kind of strict definition of it, but you know, the way we use this is PDV. So let's see what this is in terms of our P's and our V's. This is going to be the left side minus P prime times V2 prime minus V1 prime, right? Delta V minus P double prime, the left-hand side, V2 double prime minus V1 double prime. In other words, the total work done is going to be the work on the left and the work on the right. So all I'm doing is, after describing these variables in our figure, I'm just putting in those values, right? And now what we can think as an aside, just to help us here, is probably we would expect V2 prime to be less than V2 double prime, right? In other words, we're gonna throttle this gas long enough that the new volume on the right is greater than the new volume on the left. But we're going to start off with the beginning volume on the left in A is greater than the starting volume on the right, right? So we're going to start with a little bit of new pressure or new gas, but we're going to end with more, right? So we want it to be a substantial change. So we have these kind of conditions that help us. This is not necessarily going to help us. This is not necessarily going to help us. Let's see. With the math or whatever, but it's going to help us visualize what's going on in terms of these variables. So these are, what I just said can be stated in these conditions between the ones and between the primes, right? So we have these conditions. All right. Well, we know that delta U is going to be the total work, which is going to be integral of the dW, for example. That's the difference between dW and W. How about enthalpy? So what we really want is we don't want just constant heat. We want to know something about the heat at constant pressure, right? Because each side is going to be considered at constant pressure. Each side is a constant pressure process, right? In other words, if we go up and look at our pressure profile that I drew, the cartoon pressure profile that I drew, what we really have up here is constant P, constant P, P prime or P double prime, but it's a constant pressure process on either side of our plug, right? The change occurs only through the plug. So we're going to be interested in the enthalpy. All right, what is enthalpy? Delta H equals delta U plus PV, right? In other words, it equals, let's look at what it is on the left-hand side. U prime is going to be H prime is going to be U prime plus P prime V prime, right? And H double prime is going to be U double prime plus P double prime V double prime. So again, remember, the ones and twos are before and after. The primes refer to left and right, single prime, double prime, okay? Okay, so this is just all convention to make sure that we know what's going on. Well, let's write this down. And I'm going to write down something again, which I already wrote down, delta U, because we're going to use it. This is minus P prime. This is just the work from before. V2 prime minus V1 prime. All right, so this is from above, right? But now let's write down what delta H is. Now, delta H is constant. I'm sorry, P is constant on each side, right? So when we do the delta only affects the V, right? So this is going to equal delta U, right? In other words, the U1 minus U2 plus, but I'm lumping that all into delta U, P prime delta V prime plus P double prime delta V double prime, right? Right, in other words, this is delta U plus P prime V2 prime minus V1 prime plus P double prime, hold on a second, I ran out of room, plus P double prime V2 double prime minus V1 double prime. But what we see from up here, what delta U is, right? We can see that the delta U is equal and opposite to this PV term we just introduced. So what we find is delta H is 0. When we add these all up, this is called isenthalpic. Isenthalpic. So an isenthalpic process is kind of like an adiabatic process, but it keeps the state function constant rather than the non-state function variable heat, right? So it's a little bit more particular, a little bit more rigorous thermodynamically. All right, so an isenthalpic process is where delta H is 0. All right, well, in this experiment, we could easily measure the temperature in this experiment, right? Because all we have to do is put a temperature probe on each side, right? Very easy to do. Taking temperature is about the easiest thing we could do in an experiment. So we can measure this easily and directly. So this is going to be one way that we could ensure the temperature is going to be constant or relatively constant. And we feel like we know how T and P are related, right? From the ideal gas law, we know that if we increase the temperature, then the pressure should increase and vice versa. So if we plot the temperature and the pressure on the right, this is on the right-hand side, right? The cooled side, then what we should find is something like this, right? As the temperature goes down, oh, that's wrong. Hold on. We should find this kind of relationship, right? As temperature goes up, pressure goes up. But what we want to realize here, and the reason I drew that backwards at first, is our cooling process is going to travel this way. Or let me use the term that we used before, throttling. So throttling is going to kind of move down and to the, this is the kind of behavior we expect. And I made the line kind of curvy to give us some wiggle room. We know from the ideal gas law that this is a direct relationship, right? A linear relationship, but I'm leaving out some wiggle room here. We don't know exactly how this works. And in this particular plot, what we're going to say is that the T prime and P prime on the left-hand side are constant, right? So in other words, even when we first start pushing at the constant pressure and temperature from this side, like this, the right-hand side might show a temperature and pressure change until it hits the steady state, right? But so this is just what we might expect. Now let's go back to our Joule-Thompson coefficient, which we did both kind of in a problem set and the test. And it doesn't matter what we call it. The manipulation on the test, for example, it is what it is. But now we're going to see what to do with this. This is dt by dp at constant h. So this is an isenthalpic slope. This is defined as the Joule-Thompson coefficient. And if we do this, along this line, this would be called an isenthalp, right? Like an isotherm or an adiabat, but this is called an isenthalp, this line of constant H. By the way, this has the value in terms of these other variables of this, but we're not going to use this right now. We're not going to worry about this. The extreme right-hand side, we're not going to worry about this. Okay, so I think if I presented this plot to you and said, here's how T and P are related, the only thing you might say is, well, that should be linear, right? We know from the ideal gas law that that plot should be linear, but the relationship should be positive, right? The relationship between T and P clearly should be positive under most circumstances. The only thing we're not sure about is what does it mean to be isenthalpic, right? This could be a little wacky. Okay. What else do we know? We also know that H is just a function of temperature for an ideal gas. So the Joule-Thompson coefficient should equal 0 for an ideal or perfect gas. In fact, that's one of the things that we wanted to show earlier, right? So actually we showed the energy, the internal energy, not the enthalpy, but it's very similar. But because enthalpy is a function of temperature, if we hold enthalpy constant, then that should mean that the temperature derivative is also constant. Or the temperature is constant, so the derivative of temperature is 0. So so we would expect the Joule-Thompson coefficient to be 0 for an ideal gas. However, for real gases, we would expect this Joule-Thompson coefficient not necessarily to be 0. It could be 0, but we can't, we can't guarantee it at this point. Okay, it turns out for pressures, let's say around an atmosphere, 1 to 10 atmospheres, and temperatures around room temperature, the Joule-Thompson coefficient is greater than 0. And so this would fit in with my cartoon plot, right, that I showed above. This fits in with what we expect. And a Joule-Thompson expansion, in other words, throttling, will cool a gas. Okay. So let me introduce another picture here, because it turns out, of course, that it's a little bit more complicated than that. I put this picture in the wrong place, so I have to go to a different place. So many steps. Like the easier things become, the more we complain about how hard they are, right? In the grand scheme of things, that's pretty easy. Okay, so what this plot is this is a plot of Joule-Thompson coefficients versus temperatures. So it turns out, what color do I want to use here? That, oh, I can't draw on this. Now maybe I can. Here's 0. And you'll notice that on this chart, nitrogen, hydrogen, and helium all have Joule-Thompson coefficients less than 0. That means that an throttling will actually heat the gas up, right? That's what that means. So we cannot use, what this plot tells us is, we cannot use a Joule-Thompson expansion to cool a gas for nitrogen less than 600K. Okay, no big deal, right? Because 600K is actually pretty hot, right? So if we want to cool nitrogen below 600K, I'm sorry, above 600K, above 600K. That's not a big deal because 600K is pretty hot. So all we have to do is get something colder than that and it'll chill the gas, right? So in other words, we don't have to use expansion to cool nitrogen above 600K. We just have to put it in something cold, like a refrigerator, and it'll cool it, no big deal. But we do have a real problem for hydrogen and nitrogen, because the hydrogen temperature that this kind of inversion happens is 200K. This is pretty cold, right? So we're going to have a problem cooling hydrogen even at room temperature. And for helium, it's even worse. this is 40K. Helium's kind of special, right? It's worth mentioning that the helium is a liquid below 4.2K, right? And helium is a solid only at 0K, right? In other words, we're talking like milli or microkelvin, right? So helium is the most noble of the noble gases. We're going to have the most trouble dealing with this with helium. So we have a problem using regular Joule-Thompson expansion to cool a gas. So the Joule-Thompson curves themselves, there's another way to look at this. So I'm going to draw this. I couldn't find a good picture, so I'm going to draw my own picture, right? So if we have pressure and temperature, and we plot isenthalps, then what you get is you get an area that we call an inversion curve. Okay, now what we're going to do here is we're going to draw this plot here, this initial cartoon plot that I drew. We're going to draw this. This is what we'd expect, right? We're going to draw the reality. So the reality looks like this, where the isenthalps look like this. Roughly. So these are isenthalps, and out here, on the right of the inversion curve, the Joule-Thompson coefficient is actually less than 0. And in here is where the Joule-Thompson coefficient is greater than 0. And then there's going to be some T max and T min where we can work within. So we really want to work within this inversion curve. So the question, so there's a temperature range that we can work at, because we're actually going to turn it on its side. I can't really do that without screwing up the picture, but you get the idea. You can turn this plot on its side, and that gives you a region of temperatures you can work with and some pressures, right? So remember before I said at typical temperatures and pressures that we live in, we can do this for most gases, and that's within this inversion curve. All right, so what's the whole point of this? The whole point of this is to kind of describe how we might cool a gas like hydrogen or helium to the liquid, right? So in other words, we don't want to just cool a gas and make a cold gas. We might want to condense the gas. We might want to condense the gas, right? So it turns out that you can start with nitrogen. So these three gases are pretty interesting to work with in kind of a series. So the way we might do this, let me catch up to my other set of notes here. Eventually I'll get there. So the way we might do this is you can, if you start at room temperature, right? If you start at room temperature, you're below this inversion point for nitrogen. So we can cool N2 to its liquid point, 77.4 K, where it is a liquid. So we can start with this. We can start with this, but at 77.4 K, right? We're going to use, this is below the liquid point of hydrogen, but we're going to start with gaseous hydrogen, and then we could use the nitrogen to refrigerate the hydrogen. And really the way to do this, again, I just found descriptions of this, so I'm going to have to draw a picture. So here's our Joule-Thompson apparatus. And what we're going to do is we're going to put liquid N2 around the left-hand side at 77 K. And we're going to put our hydrogen in here at 77 K, right? In other words, the nitrogen is going to serve as a bath for the hydrogen to keep it at 77 K. And then we have our porous plug. And what's going to happen over here is we're going to squeeze the gas out until we get hydrogen at about 20 K, which is where it's going to turn into a liquid, right? And then what we can do, and then on this side, right, in order to do this cooling experiment, the right-hand side has to be adiabatic. So the right-hand side has to be adiabatic, and the left-hand side, we're going to use nitrogen to chill it. So now, after that, we can take out this hydrogen, and then we can do the same thing to helium, right? So we can take the hydrogen at 20 K, this is adiabatic over here, that's the porous plug. So over here, we're going to have helium at 20 K. We're going to squeeze this out until it cools to helium at 4.2 K. So we have to use these successive Joule-Thompson expansions, right? Now, once we have liquid helium, then we have to do the regular kind of evaporation that we talked about before, right? That we pump out this at low pressure, right? There's an additional complication with helium, is that helium is superfluid at about 4K. I think it's 3.8 K. It becomes superfluid. What's a superfluid? A superfluid is the liquid phase that basically doesn't have to obey the law of gravity. So it'll come out of its container. You can't put it in a container and have it stay there. It'll flow out of the container. Very strange, right? Liquid helium. Anyway, so this is basically how the Joule-Thompson experiment is useful. I think other books I've seen in thermodynamics use the Joule-Thompson experiment as an example of comparing and contrasting ideal gas behavior to real gas behavior. In other words, the Joule-Thompson coefficient is this kind of artifact of the Maxwell equations of differentiation, and it gives you some thing that you can do you can differentiate the state function. Well, for an ideal gas, this happens to be 0, and for a real gas, it happens to be non-zero. But it turns out whether it's greater than 0 or less than 0 has very important physical implications, and those usually aren't discussed. And so Joke realized this And it took him years to figure out a way to set up the experiment. But when he did, he was able to, for the first time, produce things like liquid hydrogen and liquid helium, at least at laboratory scales, right? And show other people how to do it, which is pretty amazing and important. Okay. So what happens if we want to cool other substances down? It turns out that you can't use this for everything, right? You might be able to produce liquid or gaseous helium at very low temperature, but then you have to use that substance. You have to use the helium as a refrigerant or a bath, right? You have to use it as a bath to cool other things. And in doing so, you're going to boil it away, right? So we can use, let's say we have some liquid or some gaseous helium at 2K, right? We can use this as a refrigerant to get things cold, but in doing so, it'll boil away because its liquid phase is so small, right? It's only a few K. And that's okay. So that's okay as long as we're willing to deal with the loss of our liquid helium. And hopefully we're going to be careful and capture the gas because helium's pretty valuable. But we can use liquid helium as a refrigerant to cool things. But we might want to investigate some other thermodynamic techniques for cooling. And another method Joke used was magnetization. Okay, so magnetization, it relies on basically the magnetic moment of electrons. And I think later on what I'm going to do is I'm going to introduce a couple simple lattice models to describe magnetization, where every site has a magnetization that's either up or down. And to get a net magnetic moment in the substance, you need more upspins than you need more net upspins or downspins, right? So if let's say you had a grid of 100, a square grid of 100 squares, and in each square you could put a spin that was a magnetic spin that was either up or down. Well, if 50 of them are up and 50 of them are down, then there's no net magnetization, right? Because the ups and downs cancel each other out. If it's 5149, then there's a very small net magnetization. If it's 99.1, then there's a large magnetization, right? And in terms of zero temperature, right, then as we would cool this substance down to zero temperature, then all the spins, in order to attain the one state, you remember the one statistical mechanical state that describes zero temperature? There should be just one state. It would either be all up or all down, right? So all the spins up or all the spins down would be the zero temperature state. And it's degenerate. All up or all down is degenerate, right? We can just turn our solid by 180 degrees to get one from the other, right? So it's degenerate. So this is the idea of magnetization. And it turns out that gadolinium 3 sulfate octahydrate is what Joke used to illustrate this. So let's talk about this a little bit. And again, let me introduce one more picture because this has to do with entropy and temperature. And again, we're going to spend a little time talking about this. Maybe I didn't. This is probably a picture I can draw. I guess I didn't save this picture. All right, so the way this works is we're going to plot entropy versus temperature. And this is going to be about 0K to 10K. So we're going to deal with a very low temperature area, right? And here's entropy going like this. So we get two curves. Let me start with one. What happens at 0K if all the magnetic moments, all the spins are kind of up and we raise the temperature, then the model I described to you, either up or down, is a very simple approximation of the reality, which they can go in any direction, right? And up or down gives you quite what we call a hard phase transition. In other words, since the spins can only be in two states, up or down, then the phase transition between a net moment and no net moment is pretty sharp, right? It's pretty hard. If the spins can move smoothly through 2 or even 3 dimensions, then you get a much softer transition, right? And it's much easier for the spins to move a little bit. And that's the way it works in real life. So the spins moving just a little bit requires very little thermal energy, right? And this is kind of the idea of residual entropy that we were talking about before. So if we raise the temperature, the entropy goes up. The entropy goes up like this, right? Okay. So this increase due to, let's call it spin disorder. Spin disorder. Okay. So how do we introduce the magnetization thermodynamically? Let's start with internal energy. TDS minus PDV, and we're going to add in BDM, right? So B is what's called the magnetic flux density. Another word for this is magnetization, right? In other words, magnetization is the experimental observable tied to a magnetic field, right? So in other words, aside from temperature, there's another way that we can align these magnetic spins, right? We can turn on a magnetic field, right? Now, chemists usually worry more about electric fields than magnetic fields, but in NMR, we have both, right? But a magnetic field is pretty much exactly like a magnetic, magnetic field is pretty much exactly like an electric field, right? In other words, a dipole moment is to an electric field as a magnetic spin or nuclear moment is to a magnetic field, right? So the idea is very, very similar. It's just a matter of where exactly that spin lives or occurs within a molecule or a nucleus or an atom or whatever, right? All right. So if we want to align a bunch of magnetic spins in a solid like iron, we turn on a magnetic field and it'll align them, right? So that's the thing that's tied. All right. So you can do Joke experimented with what's called adiabatic demagnetization, right? So in order to do this, what we're going to do is we're going to start at a certain point here. There's going to be a new curve, right? And let me draw this in. And it's going to be a way to cool the substance. Okay, so here's how you do it. You take some of your substance. This turns out to be gadolinium-3 sulfate octahydrate, right? And the reason they do this is because the magnetic substance here is the gadolinium. So the gadolinium nuclei have a magnetic moment. It's ferromagnetic. But we want them to be, we want these atoms that contain that magnetic moment or spin to be physically far enough away from each other that they don't interact with each other. So if this one moves, it doesn't affect this one, right? They're independent. Because if this one moves and they kind of move together, they respond to each other, then they're correlated. So what we want them to be is uncorrelated. In other words, we want them to be far enough apart that they're uncorrelated. And basically what happens is the sulfate and the water molecules give enough space between the gadolinium atoms that these magnetic moments are uncorrelated, right? Luckily, magnetic nuclear moments have much less staying power than like a dipole moment, right? In other words, the distance that they can feel each other is much shorter. So we only need a couple molecular diameters for them to be uncorrelated. So these spins have to be uncorrelated. So think about these spins at some certain temperature and at some certain temperature, which we'll label 1, right? They have some sort of motion, in other words, some entropy. What we're going to do is we're going to put this solid in contact with a liquid helium bath, okay? So at 1, we have our solid, and we put this in a bath of liquid helium. In other words, this is 4.2, this is 4.2 K, right? So that's why this temperature range is so small, because it has to be within the range of at least hydrogen's liquid area, which is very small. So we're going to put this in a liquid bath, and the bath can actually interact with the rest of the world, and this is going to be important. So what we're going to do when we move down, we're going to bring this slowly into a magnetic field. All right, we're going to slowly bring this helium solid system into a magnetic field, which is going to be down here, right? So we're going to bring it slowly in the magnetic field, and it's not a strong magnetic field, or if it's a strong magnetic field, we're just going to come on the periphery. And what this is going to start doing is aligning these spins. Let's say the spins start to organize more. They're going to be more aligned. This is going to lower the entropy, right? Now, in order for this to happen at constant temperature, some disorder, some heat has to be dumped to the helium, right? And so what happens is some He boils away. Okay, so what the helium is there for is to carry off, in a sense, this entropy, dq over T, right? dq over T. And the T is 4.2 K. So what this does is it takes us to 0.2, right? This is not the adiabatic part, right? The adiabatic part, because we're allowing heat exchange. The adiabatic part comes next, right? This process is called, let me write down what it is called, right? This is called isothermal demagnification. Isothermal demagnetization, not fication, magnetization, right? Isothermal demagnetization. So in other words, we're lowering the net magnetic moment of, that's not demagnetization, is it? We're ordering the spins, so it's actually isothermal magnetization. We're increasing the magnetic moment of this substance, right? Okay, so that's what happens to 2. Okay. Now, the next part that we do is we're gonna take away the helium. So now we just have the solid. And then we're gonna slowly move this, we're gonna slowly move the solid away from the magnetic field. This is going to be a reversible, right? That's the slow part. Adiabatic, right? Because whether or not our solid now is in the air or actually insulated, it's adiabatic, because air is a pretty good we would say diabatic wall. Air itself is a pretty good insulator, right? So it's a reversible adiabatic demagnetization. Right? Delta S is 0 because it's reversible and adiabatic, right? If it's adiabatic, there's no heat exchange, it's reversible, then we get the dq over T equals 0, right? And we're moving to the left. Okay, so the question is, how can you use Maxwell relations? What time is it? Good. How can you use Maxwell relations and stability to predict our observables? In other words, what happens in an experiment? Okay, well, if we're going to do a real lab situation, we want constant pressure, So let's look at enthalpy. And let's also, we want to look at the change in the magnetization, right? Not the change in the field. So we're going to do a Legendre transform. The constant pressure part is easy, right? Because what we're going to do is we're going to use H. But we're also going to change our focus, change our independent variable from the magnetic field to the magnetization, because we know we're changing in the magnetization now, and the limit of, if it's reversible, another way to think about that is that the magnetic field at each step is constant, right? So we're moving it slowly through, away from the weak magnetic field, that the change in magnetic field is constant. So that's effectively, the magnetic field is 0. So we need to do a Legendre transfer. So we're going to minus off Bm, right? What this gives us is, it gives us kind of a new enthalpy, right? This is going to be called, let's call this the magnetic enthalpy, right? It's really just going to be the enthalpy with this extra term. So what we get from this is we get a reciprocity relationship. Let's do constant P dt by dB at P equals minus dm by ds at constant P. Okay. Now, this does not necessarily tell us the sign of one or the other, because what you have to do now is we have to have an experiment, and the experiment is going to tell us the actual slope, right? So in other words, the way we're going to use these relations is if T versus B was like this, then dm by ds is greater than 0, right? Because what we're saying is the left-hand side is negative. If the left-hand side is negative, the negative sign takes care of that. So the actual partial derivative has to be positive. If T versus, and this goes for any relationship like this that we're going to use, these stability relationships. If we have this case, then the left-hand side is positive, and dm by ds has to be less than 0 in order to make it work. Does that make sense? So it's not enough just to have this relationship, have one tell you the other. You also have to have the experiment that tells you whether the slope is positive or negative. Okay. Okay. Well, what we did in our experiment is we found out that as we turn down the magnetic field, the entropy, I'm sorry, we found that dm by ds was negative, right? So I had these, I turned these around, right? So this is the first time I'm really presenting this, so I did backwards. So what I should have done is m and s, but it works backwards, right? So what we found is this, or what we find is this. So that tells us necessarily that dt by dB is greater than 0. Okay. So adiabatic demagnetization is a constant entropy process, right? We're going this way, right? Horizontally, the second step. Adiabatic demagnetization is constant entropy process, which the net magnetization decreases, and thus the temperature also has to decrease, right? So it's kind of like a three-step process, right? This is the first step. The relationship is the second step, which gives you this. But then the experiment that we did, we lowered the net magnetization. In order for that to work, the temperature has to go down. Now we can see that from this cartoon picture I drew, right? So we started kind of backwards with the picture and developed the idea. But the take home from this is that adiabatic demagnetization will cool the substance too. Okay. There's another way to look at this that's more tied to entropy. And this is going to be more reinforcing rather than new. So let's go along with that. In order to involve entropy, we need dg, right? Free energy. So we're going to end up with dg prime. We're going to do the Legendre transform. to get constant temperature. Constant temperature, right, is going to give us the entropy. In other words, the independent variable being temperature is going to give us entropy. And we already have the P involved for enthalpy, and we're going to do the Legendre transform with the magnetization we just did. Basically, we're just going to do the SDT transformation. So what we get from this, the Legendre transform of S and B, we're again going to hold P constant, and T and M, right? So we're going to find ds by dB at T and P equals dm by dt at B and P, right? In other words, there's a positive relationship between these two, right? So if we lower the magnetization, we're also lowering, the magnetic field at constant B decreases with increasing temperature. So this is less than 0, right? So if B goes down, S has to go up, right? But again, this makes sense, right? This is kind of where we started off. If we define the net magnetization as a function of how many of these spins are aligned, right? The more spins that are aligned, the higher the net magnetization, then it kind of makes sense that the more the spins are aligned, this is our more organized, right? Organization is kind of a qualitative description of entropy, right? We would say that something that's more organized has less entropy, right? So again, if we lower the net magnetization, the physical manifestation of this is spins being more random. Spins being more random means greater entropy, right? So again, as I said, this is more reinforcing the whole concept of this rather than being enlightening like the first one. So, but one thing you'll notice, and I'm not sure if it's super clear from this diagram, so let me draw another one. There's a limit to adiabatic demagnetization. So let's look at this curve again. Looks like this, and the lower curve looks like this. So this is greatly expanded. So basically what we're doing, this is kind of similar to, you know, in organic chemistry, when you do a distillation in a column and you get theoretical plates, right? And we're going to see how this works in, from a physical chemistry standpoint later in this semester. But basically what you're doing is you're going like this. So there's one step. Then you come down here like this, and here's 2 steps. So you can lower the temperature, but you have to kind of go in these 2 steps. But what happens when you come down here, there's a limit. There's a limit to how many times you can kind of stair step down this lens, this lenticular difference between these 2 curves, right? And I think the book says that this is 0.0015 K, 1, 2, 3, which is 1.5 millikelvin, or 1, 2, 3, 4, or 1500 microkelvin. So for the gadolinium sulfate hydrate, the limit is about a millikelvin, right? And so this is one of the this is one of the physical reasons why we cannot attain absolute zero. It's just not, Mother Nature is just not allowing us to get that low. Okay, so that brings us to the end of today. This was kind of, in a way, this was kind of in the weeds, but what it does is it gives us a physical connection to some of these thermodynamic quantities we've been doing. I hope you could see the physical connection, right? The physical connection is a very real need or desire for chemists and scientists to attain low temperatures, right? At least you at least want to be able to condense helium to a liquid. So now we can use the helium as a refrigerant to get other things cold. And it doesn't necessarily mean we need to get everything down to 4.2 K, right? We can use it as a recirculating refrigerant to get it down to maybe 50 K, right? And so this just is one of the uses of thermodynamics and physical chemistry, is to show people how you can get this, and then hopefully a talented experimentalist can figure out how to actually do it. Okay, so I think on Friday we'll just have kind of like a problem solving session, and we'll just see how it goes, kind of free form. I want it to be more engaging, and I want people to try things out. So it's going to be kind of like the thermodynamic. I hope it's going to be like the thermodynamic equivalent of a high school shop class, where some car dealer donates a car to the auto shop class, and you just kind of go in and take things apart and put them back together and see if the car runs. So that's kind of what we're going to do. We're going to kind of try to dive into some of the math and not be scared of breaking things, and just trying to gain a little bit of experience with some of the manipulations. Okay. Does anybody have any questions? I wasn't paying attention to the chat, so yeah.